In section 8.2, we're talking about the graphs of polar equations. A lot of times we're just going to do this on our calculator, but I do want to show you how it is that these graphs come to life. Now we're going to start with some simple graphs. I'm going to start with the graph of r equals 3. Now, in order to do this in your calculator, a couple of things of note. First, you need to go to the mode on your calculator, and you need to change the fourth line down to be pole, P-O-L, which is for polar coordinates. And don't forget that you need to be in radian mode as opposed to degree mode. Now, the graph of r equals 3 is a circle. The reason that it's a circle is because if you remember that r squared is equal to x squared plus y squared, and you go and you change this polar equation back into rectangular coordinates, you would first square both sides, and then r squared is x squared plus y squared. So this would be a circle whose center is at 0, 0, and whose radius is 3. So the graph of this polar graph would look like this. And when you graph it on your calculator, that's just what it looks like. But we need to talk about some more complicated graphs. So let's move on to something else. Now, not only can we have graphs that say r equals, when we deal with polar coordinates, we're also dealing with theta, because all of our ordered pairs in polar coordinates are r comma theta. So sometimes you can get something like this. Let's talk about the graph of theta is equal to pi over 3. Well, if you recall that tangent theta is y over x, and this is something that we used when we were changing between rectangular and polar coordinates. If you do the tangent of pi over 3 is equal to y over x, and then solve for x, you get x times the tangent of pi over 3. And the tangent of pi over 3 is the square root of 3. So the rectangular graph is just the graph of y equals the square root of 3x. Well, that's just a line. And that line looks something like this. Let's see, if it's square root of 3x, it goes through 0, 0, it goes through 1, square root of 3, it goes through 2, something else. It looks kind of like this. But the other way of going about graphing it, if you think about your polar coordinates, in our polar coordinates we have all of our special angles. Theta equals pi over 3. Pi over 3 is this line here. So there you would go. And it looks like the same graph I got if I changed it into rectangular coordinates and then graphed it. Let's start to graph something a little more complicated, like r equals 2 sine theta. Now, if you're doing this by hand, the way that you're going to go about doing it is you're going to plug in every special angle starting from 0 all the way to 2 pi for theta, and then you're going to solve for r. Now remember that when we graph this, the ordered pairs are really r comma theta. But the way that we go about graphing a polar coordinate is first you go to the angle, and then r represents the radius from the center. So here are the decimal values you'll get if you plug in each of these theta values. I want you to look at the pattern in the numbers here. Remember, if you think about the quadrants, when you take the signs of numbers in quadrants 1 and 2, everything will come out positive. And when you take the signs of any angles in quadrants 3 and 4, you'll get negatives. Now, when we talk about polar coordinates, the negative radius tells us to first find the angle and then go the opposite direction, which is a little bit different. So now let's talk about what the graph of this looks like. Now, even though the graph that I've just pulled up has degrees instead of radians. You should be familiar with how the radians work. And also, I don't like how small these little circles are, the 1, 2, 3, 4, 5. We need to make these a little bit bigger in order to get a better idea of what's going on. So I'm going to make, let's see, 1, 2. I'll make this my radius of 1. And this be my radius of 2. Just so I can have a graph that looks a little bit nicer. So we'll call this 1. We'll call this 2. Alright, so now let's start. At an angle of 0, we were at 0, which is the origin. At pi over 6, we were at 1. So here was pi over 6, and then we go 1 radius out. At pi over 4, we were at 1.73, I believe. Let's see, 1.41, I'm sorry. 1.41, let's see if that's 1, and that's 2, then it'd be probably around here somewhere. And then at pi over 3, we were at 1.73, so that would be a little bit closer to 2. And then we were at 2 at pi over 2. And then it started going back down, so at 2 pi over 3, 3 pi over 4, 5 pi over 6, and then, let's see, and then at pi we were at 0 again, so we started back here. Well then, at 7 pi over 6, we're at negative 1. When you go out to, say, here's 7 pi over 6, negative 1 just tells you to go the other direction, so it'll be back over here again. So all those negative angles are just going to repeat the dots I've already got. And this is what you end up with, is this circle that's above the x-axis. Well, that's kind of interesting because now we're going to talk about a pattern about graphs of r equals sine theta and r equals cosine theta. So, for r equals a sine theta, the graphs that you're going to get will either be a circle above the x-axis if a is positive, or it'll be a circle below the x-axis if a is negative. Cosine will be a circle to the right of the y-axis if a is positive, and it will be a circle to the left of the y-axis if a is negative. Well, not all the graphs of polar coordinates are circles. Sometimes they're going to get some very different shapes. Let's talk about that. I want to graph this polar equation. R is equal to 2 plus 2 cosine theta. And I'm going to do the same thing again. I'm going to plug in all the numbers from 0 to 2 pi and find out what the radius is from the center. I'm going to do that very quickly so it'll just pop up on your screen. So here are the values. So I want you to notice that the maximum distance away from the origin is 4. There are no negative radii here, so I don't have to worry about going to an angle and then going the opposite direction away from the origin. Now we're going to go graph this. I apologize for the really bad circles. Instead of going up to 10, I drew this so that there are 4 circles. So there's a maximum radius of 4 away from the origin. So when we started this at an angle of 0, we were at 4. So I'm going to put at 0 my 4. And then at pi over 6, it was like 3.71. And then at pi over 4 is 3.41. So it was probably about there. And then it was at 3. And then it was at 2. And then it was at 1. And then at 3 pi over 4 was at 0.59. So it was probably in here somewhere. And then it was at 0.27, which was really close to the origin. And then at 1 pi, it was a 0, which is the origin. And then at my 7 pi over 6, it goes back out again, 0.27, 0.59, 1, 2, 3. Let's see, 0.27, 0.59, 1, 2, 3. And then, let's see, at my 7 pi over 4 was at 3.41, and then it was at 3.73, and then back to 4. So 3.41, 3.73, and then back to 4. So here's what my graph looks like. Looks like it was kind of circular shaped, but then it had this little dimple. Well, when a graph looks like this, it's called a cardioid. Sorry, I need to pronounce this right. Cardioid. And any equation for polar coordinates of the form r equals a 1 plus or minus cosine theta, or r equals a 1 plus or minus sine theta, will have this shape. Now, whether it has a dimple on the left, a dimple on the right, a dimple above, or a dimple below, depends on whether it starts with a negative or if it's sine or cosine. So let's look at each of these individually. If the polar coordinate is r equals a times 1 plus sine theta, the dimple will be at the bottom of the graph, and I want you to notice that most of the graph tends to be above the x-axis, kind of like it was with those circles. If it's r equals a times 1 minus sine theta, the dimple will be at the top of the graph, and most of the graph is below the x-axis. If the graph is r equals a 1 plus cosine theta, the dimple will be on the left side of the graph, with most of the graph being to the right of the y-axis. And if it's r equals a times 1 minus cosine theta, the dimple will be on the right side, with most of the graph being to the left of the y-axis. Let's talk about what happens in these graphs when these two values are not the same. In the last graph, if those two values are the same, then we get this little dimple in the graph. But what if the value that's independent of the cosine or sine is smaller than the one being multiplied by the sine or cosine? What we're going to get are these loops inside the graphs. And these little loops are going to make our equation or our graph be known as a limacon. I have a neat little word here. So when r is equal to a plus or minus b cosine theta, or r is equal to a plus or minus b sine theta, if a and b are not the same value, you're going to get these loops. Well, we don't even have to graph this next one by hand. If you want to just plug it into your calculator, my recommendation is after you plug it in, hit zoom fit. That seems to show the graph pretty nicely. So the graph you get looks something like this. Let's see. Probably not doing it justice, but you get something that kind of looks like this. I want you to investigate what happens as you make this number bigger. It's very interesting what happens, or what happens as you make that value smaller. I just realized I don't think I was playing this while I was trying to do this particular graph. The graph of anything of this format, where a and b are not the same value, is called a limacon. And instead of graphing it by hand this time, I'm going to graph it on the calculator. And if you graph it on the calculator and you hit zoom fit, you're going to be able to see the entire graph on your screen. Or if you use the website that I had given you, that one works just fine as well. What I want you to do is I want you to investigate what happens as you change this value. Make it bigger, make it smaller. Watch what happens to the loop inside the graph. It's going to change, and it's very interesting how it changes. The last type of graph that we're going to look at right now is this. What happens when you multiply the input by a value? Well, we're going to get a figure called a rose. It doesn't really look like a rose. I don't know why they call it a rose instead of a daisy. I think they should just call it a daisy. And the number of petals that this graph will have is dependent on this value, and is also dependent on if it's sine or cosine. So right now, if you just graph this in your calculator, you get this graph. You get this pretty little four-leaved rose. I'm not sure they write it leaved. And if that number is an even number, we'll call it n. So if n is even, you're going to have 2n petals. If n is odd, you're going to have n petals. So in this case, because n was even, you would add 2 times 2 petals, which was 4. And I want you to notice what the graph of cosine looks like. Now let's talk about what the graph of sine would look like. If we have a sine graph, and n is an even number, then the graph is going to look like this. It looks a little bit different from the cosine one. The cosine one, the 4 petals were on the axes. Notice that in this case, the petals are in the quadrants. If n, however, is odd, let's say n is 3, and it's a sine graph, your graph would look something like this. For cosine, when n is even, as in the example we just did, we saw that the petals looked like this. And if n is odd, if we say n is 3, the graph is going to look like this. Now, are you going to have to memorize all this stuff? No, you're probably just going to do it in your calculator, and that's fine. However, what I would like you to know is have a general sense of what the graph's going to look like before you actually ever put it into your calculator. And that's going to help you out. This is an introduction into graphing polar coordinates. And the next video will be on sets of symmetry.